Okay, assuming our objective is to pull out the elements of the Mueller tensor from measurements of the Stokes vector for doubled frequency or some other intensity-dependent observable as a function of the input polarizations, then we run into a bit of a problem using the tensor notation, because it's going to be difficult to mathematically invert in using linear algebra in order to isolate the elements of the Mueller tensor themselves. So the topic of this little snippet is vectorization of the Mueller tensor. So we'll turn this into something where the M can be pulled out in a vectorized form and then solve for it using linear algebra. And I'll start, before going into vectorization of tensors, briefly review vectorization of matrices, because that will serve as the foundation. So for vectorization of a matrix, the vec operator is well established, and this is the order of the elements that emerge from the vectorization operation. In vectorization of matrices, it's not difficult. There's no controversy over the ordering of elements at all. Turns out when you get to tensors, it does start to be a bit interesting in terms of the fact that you don't necessarily know which particular elements should go in which particular order unless there's some pre-established convention. So we're going to build that pre-established convention using an ascending vectorization format, and that's indicated by the arrow over the tensor. So in the ascending vector format, the tensor elements always increase in binary form. So when considering the vectorization of the Mueller tensor, for example, we know exactly, if we use this ascending vectorization notation, the order in which the indices will appear in the vectorized form. And they'll be 0, 0, 0, 0, 0, 1, 0, 0, 2, 0, 0, 3, and then 0, 1, 0, all the way down to 3, 3, 3. And that'll be the full set of 64 in ascending vectorized notation. Now, there's a couple of key advantages to moving to a vectorized format. First is that we can isolate and solve the elements of the Mueller tensor using linear algebra if we take advantage of some identity relations that apply to vectorization operations. And these are the two that we'll use in this little snippet. The first pulls out the beta 2 tensor, or the second order tensor, no matter what it is, whether it's chi or whether it's the Jones or Mueller tensor, and it allows you to isolate it from it pulled out of a tensor notation. And you can immediately see, once it's in this sort of a format, if you can somehow invert this matrix, then you'll have all the elements of the Mueller or Jones tensor isolatable and solvable. And that's a key advantage. And in fact, there's another relationship that builds on that exact same framework. Instead, if you have a matrix out here to the left of the beta 2 tensor, or the B2 tensor element, B2 tensor, then instead of the identity, you can now replace it with that matrix and isolate it in the exact same way. So these are really useful identity relationships for pulling out and isolating the tensor elements. So how does this play out in terms of the Mueller tensors? Well, let's look at the first one, where we've got a tensor element double dotted into two vectors. And when we vectorize that, both sides of this, the left side, of course, is already in a vector. If we vectorize the right side, then we have this notation, which is a step toward inversion. Now, we're not all the way there, because we have a vector here of length 4 and a vector here of length 64. But we have ways of reducing this and expanding this in order to allow inversion, which we'll get to, I think, later on in one of the subsequent presentations. Right now, this is just to provide an overview of how vectorization works in general. So for the rotation operation, this is just another example of how we can use vectorization to simplify and reduce the number of elements inside the Mueller tensor. If we know that we have a smaller subset based on the discussion of symmetry in one of the preceding talks, then we can, for example, in the case of uniaxial symmetry, there might only be 20 elements in the local frame Mueller tensor, and we can populate the full set of 64 with the symmetry matrix, rotate that into the laboratory frame, and then consider what happens as we apply different polarization states and measure the second harmonic coming out in the polarization state of the double light. And then if we make enough of these measurements, we can invert this whole mess and solve for the local frame Mueller tensor. And that's really the way that we're going to be handling this. There's, of course, that's one way to simplify things without needing to assume anything with respect to the purely polarized or any model for the depolarization. If we want to connect the Mueller tensor and Jones tensors, and the vectorization is also a very convenient way to do so. So this is the relationship we have established previously, connecting the Mueller and Jones tensors. In vectorized form, we can rewrite that as this relationship. So the ascending vectorization, vectorized form for the Mueller tensor is related to this product of A terms, Kronecker product of A terms, and the ascending vectorization of the Kronecker product of Jones tensors. Now, we've actually seen something that looks like this many, many times in the discussion of the Jones framework, Jones measurement frame for polarization analysis, which is not exactly the same thing that we have from this vectorization of the Mueller tensor. And they differ just because they have the exact same terms in them. You can see you've got the Kronecker product of two Jones tensor elements, but they're just rearranged in a slightly different order, which is sort of a pain. But there is a way to get around that. If we can define an elementary matrix that will resort these, then we can get the set of products of Jones tensor elements that are given from the Mueller tensor architecture and relate them back to that framework we've already well established in terms of the Jones architecture. And if we can do that, assuming we can figure out what this E matrix should be in terms of how to resort the tensor elements, then we can now directly relate the ascending vectorized Mueller tensor to this already working framework in terms of the Kronecker product of Jones tensors. And so that's really where we're going to go next. The next step is just figuring out what this matrix E is all about.